Okay, hello. My name is Alex Staples, and today I'll be teaching you how to use energy methods in beams. So, what is the benefit of energy methods? In the case of something, let's say, of a simple beam, we could just use the force applied here to determine the deflection here. But what if we didn't have a force? What if we didn't have a force at the end of the beam and a force here? We could determine the deflection once again at this part of the beam, and we can determine the deflection at this part of the beam as well using angles, or we could use energy methods. The main method we'll be using is Castigliano's theorem. This method is very useful because it not only can it be used on straight beams as I drew earlier, but it can also be used on beams with, let's say, a curve in them. And usually these curved beams have to be thin beams, unlike the straight beams. So Castigliano's theorem can be used on a beam when the force is acting on an elastic system subject to small deformation. So it also can only be used for small deformation. So Castigliano's theorem is pretty much the partial derivative of energy over partial derivative of a force. And there's four different main methods that we can use or four different energies that we can use in this Castigliano's theorem. Those energies being, first, a bending, second, torsion, third would be transverse shear, and fourth would be tension and compression. Sorry, we're not room there. Okay, so of these four, today we will be focusing on bending. Now, each of these has their own equation to find U, or the energy, in our Castigliano's theorem, so the partial of U over partial of F. Bending specifically, U is equal to m squared, which would be the moment, times L over E I, 2EI. So that would give us the energy. Now, to solve for deflection, we need to take the integral of the energy we're giving. So if we were to take the integral, then we have deflection is equal to the integral of, and we're going to move the partial derivative to the inside of the integral. So then we get m over EI, since this would have become 2m when we took the partial derivative of the m, and it would cancel out this 2 there, times the partial of energy over the partial of force to dx, the length of, but if we were doing a straight beam, the straight part of the beam. Or let's go again. So x could be any, if this was our beam, and it had length L. X would be any length you choose from either right or left hand of the beam, it doesn't really matter. And X would be any length here, so if any length to the wall. But if you had like a force here, it'd be any length from where you cut it, if we're going to cut here, so it'd be the length of this cut. But if we were dealing with a curved beam, this would slightly change, and it would then equal, the deformation would then equal the same beginning, M over EI, and the same partial, but then we also add in the radius, and we're now integrating with respects to theta, since we have the curve member, and of course any curve is going to have, this is top part. Any beam, remember, that would have a curve would have an angle theta. And usually, 0 to pi, or 0 to pi over 2, 0 to pi over 4. So let's do an example real quick. Okay. So we're going to do a curved beam example, curved thin beam example, so that the main forces the main energy we use is bending energy. Because if it was thick, there would be some other, you'd have to use either shear, transverse, or torsion or something. Okay, so that is the drawing, and we are given that this is equal to L, this is equal to R, and these are all just variables. We're not solving numerically, we're solving, and we have a force here, P, and we want to determine deflection at this point, which we will call point C for now, because that's what I want. Or we'll call this point B because there's 4 points, because there's the point here which the force is actually directing on, at the beginning of curve B, and we have the end point A. So we have A, B, C, D. Now, since we do not have a force here, that's where the Castigliano's theorem really begins to shine. If normally with our methods, we would not be able to solve this at all, since it's a curved beam, because we won't, the angle that this deflects because of the P force, which P is the only place we can solve for deflection. If it was a straight piece, we cannot determine an angle to determine how much that would deflect like we would do in mechanics of materials. Instead, we have to apply another force, a fictitious force Q, at the point where we are trying to solve for the deflection. And in this particular problem, I just want to solve for vertical deflection. So my Q is going straight down, similar to P. And just like as in mechanics of materials, we will need to cut this piece though, because we cannot determine with multiple forces on one part. So I'm going to cut it here, and I'm also going to cut it, let's say, here. So we have 3 parts we need to determine. I'll label those. 1, from here to here, 2, and the remainder, which is pretty much the whole thing, 3. So let us start with part 1, or cut 1. So here we have D, there, We have our fictitious force Q, and this is D, and we know we have some radius of R from here to there, from wherever the center. As you can see, it's not perfectly aligned with the cut, because if it was, then we have a force P there as well. So now what we're going to need to determine is the moment right here, and put our moment clockwise so it's positive. We need to determine the sum of the moments so we can figure out what this moment is exactly. So we're going to do the sum of the moments is equal. Right away we know that that moment, so we just have the moment is positive. But now we have whatever the moment caused by Q would be, which would be the length, the X, we'll call it X since there, the length from here to here, but it'd be like we need to find this distance right there, because that will give us that times Q will give us the moment it applies onto the beam. So in this case, we need to figure out, we can't just say this is 6 or R, but what we can figure out is that from this point to where we cut is also equal to R. So we've made a right triangle, and as you can see, since we also know this is R, the cosine of the angle here would be equal to this small portion we don't know, and the portion we need is the difference between the big R and that small portion. So we do cosine, we do R minus R cosine theta. And then all of this is equal to 0. So now we got that, we can determine that the moment for this piece is equal to negative Q R minus R cosine theta. And that's just for piece 1. Now for piece 2, where do you go write this? I'm just gonna, I don't know if you can see, but I got more down here. I'm just gonna put all my moments down here. Yeah. So moment 1 is equal to negative Q R minus R cosine theta. And theta, in this case, is less than or equal to 0, which is less than 90 degrees. Because as we can see from our drawing, if cosine was, if this angle was 90 degrees, we'd be at the P area, which would be part 2. Okay. Okay, now we'll move on to part 2 here. So now we're not just taking in between this cut and this cut. We have to take all the cut we had before plus this new cut. So the new piece shall look like this. And we have C, D with fictitious force Q. We have force P here. And that is it. Oh, we also have this new moment here. So we're going to do the same exact thing. Sum of the moments is equal to M, once again, plus, and I'm just going to go down a line here, so I'll just M plus Q. So now in this case, Q is not just R plus whatever, or R minus cosine theta, because we have this whole distance R. We know that there's at least one R between here and here. So now we need the distance between the center to the left, which would be same thing, this distance. And we know this is equal to r. That's 90. So here's our new theta. And once again, theta is less than or equal to, or less than 90 degrees and greater than or equal to 0. So in this case, our q, the moment for q would be r plus sine theta. Plus r sine theta. You can see that since this is the angle theta, our x value would be the far end away from the theta, which would be the sine of theta, and this initial r. But now we also have the p force, which once again will be positive in this case, so plus p, and that will just be p times r sine theta. Pretty simple there. Then when we solve out for the moment, it'd be negative. Both these become m equals negative q r plus r sine theta and minus p times r sine theta. So once again, I'm gonna write that down here just to remember it for later. Messing up a little bit, but it's all good. On to the last part. So the last part will be up to anywhere but the wall. So we'll go here, down and around. Once again, we have our fictitious force Q, our true force P, and we have nothing new added here. We should have more chalk. So in this case, we will be changing it ever so slightly because now we have this distance, which would be, as we talked about earlier, an x distance, because this distance will expand however we want, if up to the wall, pretty much. So in this case, once again, sum of the moments, and that is equal to m plus q, and in this case, we have two whole r's before we get anywhere close to x. So we have r, or 2r, plus x. And then we have plus p, and in this case we only have one r plus x. And that's it. So the only difference here is now x is less than or equal to, or is greater than or equal to 0 and less than L from above. So once again, swing down here, write it down so I don't forget. M is equal to negative q 2r plus x minus p r plus x. Whew. So now that we have everything, I'm gonna erase the deck. I'm gonna erase this hole on the board. Okay, so now we have our three moment equations. But what we don't have is the partial derivatives of the moments. So in this case, we're gonna start solving out, and what I would do here is draw a little, I guess, dq, or no, du over dq. dl over dq. Draw a little thing out here, and I'm just gonna go 1, 2, 3. So if we look at the first one, hopefully you can see, if we were to, q is equal to 0, since it's a fictitious force, there's no true force, so there's no additional moment added here. But when we take the derivative, since we do have a q, we get r minus r cosine theta. And now you just go through and do it for the rest. Part 2, the first thing, the negative q cancels because it's 0, and we get p sine r, p times r sine theta, negative p, negative. And then here, once again, we do have a q, the p disappears because we're only taking the derivative in respect to the q, so we get r plus r sine theta. And for part 3, q disappears, we get negative p r plus x, capital R, and the derivative, the p disappears, goes to 0, so we get 2r plus x. Now that we have these, we can plug it into the deformation equation from earlier, which was the integral of m over ei. And so in this case, we have 2 where we have a angle and 1 where we just have a length. So we'll start with the length part because it's just easier. M over ei, and we have the partial of m over the partial of q times dx. So since this is part 3, we start plugging in numbers. This can all come out, so we just have, or no, it can't all come out. The 1 over ei can come out, and then we just get negative p r plus x times 2r plus x. Dx. Pretty sure that should be the right one. So we took out 1e over e. P is also constant, so we can remove that as well and make this p. So inside we have 2 equations with respect to x, so we have to derive, well, they're both negative, so let's just fill out the negative sign as well, make it positive, make it a little bit easy. Oh wait, no, that's a multiplication. No, it's not. No, it's not that, so we're going to keep the negative on the inside. So we move on to our next one, distribute. So we have 2r squared plus 2rx plus rx plus x squared dx, p over ei. From here, it's pretty, and then we also, since we know the x has to be less than L and greater than 0, we can put in our bounds right there. And now we just do our simple integration with each of the x's. So we end up getting p over ei, this is my integration area, 2r squared x, these two can be combined to become 3rx, so it'd be 3 over 2 rx squared, and then x squared would just become 1 over 3x cubed, and then we need to plug in from 0 to L. This here. So then once you plug in the 0 and L, obviously all of the zeros cancel, so you get nothing there but the L's. Plug in, and we can simplify this a little bit, so then we get p over ei is equal to 1 over 3 L cubed plus 3 over 2RL squared plus 2R squared L. And this would be P times. And that would be the deflection caused by the deflection on D caused by all the parts combined. You would also have to do it for part 1 and part 2. Hopefully you can do that on your own after watching this video. And after doing all that work, you would get that the total deflection at D is equal to the deflection of part 1 at D plus deflection of part 2 at D plus deflection of part 3 at D. Once you got all this together, you get the total deflection at part D. Bam, you know how to use Castigliano's theorem.